Welcome to Breadboarding. This is video 9 in the Breadboard PC series, and in this video we're going to be adding the 7-segment LED display and keypad. So this is a step necessary for us to be able to get a basic monitor, a very simple operating system running on the computer, so that we can then go on to add all the extra items that we need to be able to make a basic floppy disk booting PC. This is the original Nanocomp schematic diagram from Wireless World, July 1981. This was what was the basis for the Nanocomp 6809 project, which there will be links at the top of the screen and in the description below the video. This was a very simple computer with a built-in keypad and display, and so minimizing the chip count was one of the key design drivers of this, and so there were some simplifications which have made things a little more complicated than they perhaps would otherwise be. So what we have here is the Peripheral Interface Adapter. So this is the Motorola 6821. Basically just provides two bi-directional 8-bit ports with a couple of extra control signals. Now we're using port A bits 0 to 6, we don't use bit 7, and port B we're just using the bottom 4 bits 0 to 3. One thing to note if you're ever looking at this is that the original software that was used for the Nanocomp monitor actually reversed the A1 and A0 lines between register select 0 and register select 1, and this has caught me out a number of times during the project. So in this I'm going to map A0 to RS0 and A1 to RS1, and we'll make the changes in the software. Should also say that this BCD decoder, the 7442, was replaced in the Nanocomp 6809 project with an equivalent part as 74145. It had slightly higher current driving capabilities, and you can see here that we have 6 7-segment displays, and we also have 4 lines which go down to the keypad. And the way how this works is that when we're scanning the keypad, the input lines here will be pulled high internally by default, and if we put a 0 on one of the register scanning lines here and a key is pressed, then the corresponding pin, so PA0 to PA5, will go low if the key is pressed. When we're looking at keys being pressed, we're looking for one to go low to indicate the key's being pressed. And similarly, these are common cathode LED displays, so that means that the common pin here needs to go to ground or to low in order for the display to light. And by default, all 7 segments are actually pulled to 5 volts. The resistor we've reduced in size to 220 ohms. We don't need quite so much current for these modern displays. What this means then is that in order to turn a segment off, we actually have to turn on one of these transistors, Darlington transistors here. So it's a little unusual in that by default, with zeros coming out of the port here when it's in display mode, then we will get all the segments lit, and if we want to turn any segments off, then we need to provide a 1 on the port. So you'll see in some of the software that a lot of the data going out to the port will be complemented or inverted just before it's sent to the port. But that meant that it's a lot simpler. What I have done by using this particular chip, we ensure that the current syncing requirements for this pin here do not exceed the chip's capabilities. The chip's able to do about 80 milliamps per pin. So let's just have a look at the data sheet for the 6821. So this is a Motorola Peripheral Interface Adapter, so it provides the 2 parallel ports, port A, port B, the standard D0 to D7, the Motorola E-clock signal which we added to the PLD in the last video, read write, a low reset, so when reset is low it resets the chip, and as we said we've got the register select 0 and 1. We won't be using the interrupts or any of the other CA, CB lines for the moment. And there's one thing we really need to check here. On port A, you see here that port A in input mode, the internal pull-up resistor on these lines represents a maximum of 1.5 standard TTL loads. So it means if there's nothing input on port A when we're reading it, then it will default to 1. And that works well with keyboard. So if you just have a quick look at the bits that we're going to be using for building this. So we'll be adding a couple of breadboards at the bottom of the current design. We've got the 6821, now this is a B series part, so this is capable of working at 2 megahertz, system clock 8 megahertz, so this should be more than fast enough to catch up. Then we've basically just got our 74LS145, the PLD, the Atmel 16V8B, I think this one in particular is, And then there's the Darlington drivers, the ULN2803A. Now, I'm going to be using some 7-segment displays like this, but because I had already built some of these in the early version of the project I did before I started videoing it, then what I'm going to do in this one is make use of boards that I've already built. So this was a board that I built probably about 2 or 3 years ago when I first started this. I'll show you the design in fritzing, which is a tool that I showed in the previous series, and is quite good for doing layouts, single breadboards and Veroboard type strip board. The other thing I should say is what I'm using for the filter here is the tip I saw online somewhere to use car auto lens repair tape. So this is tape you can buy from car repair shops for repairing the sort of the lights on your car. So if there's a crack in it, you can just put this over. But this actually works quite well. I was finding it difficult to try and find a bit of plastic, big enough red plastic filter to go across the whole display, and it was going to cost like £15–20 for a bit of plastic to do that. So using this tape actually works really well, so that's a good tip. And then we're also going to be using this keypad. Again, this is a first generation keypad I produced before the one I did on the video in the Nanocomp 6809 series. It's almost identical design, and again I'll be sharing the fritzing layout, and some of the slides I've got later on in the presentation basically show some of the color coding and stuff I used for doing this. Again, it's very fiddly. I think even when I speeded up the video in the previous one, it took quite a while to actually make these. I think elapsed time, it probably takes about 3 or 4 hours to go through, do this and test it. So the fact that this is already working and tested will save quite a bit of time. The only thing I will do probably is add another connector on the edge here, just so I can put the cable in from either side. So that's going to save quite a bit of time using those. Okay, so there are a few issues with the LED display pin mapping. So the LED displays I'm using have the A, B, C, D, E, F, G, whereas the original Nanocomp design used A, B, C, D, E, F, G. So the E and the F are reversed. So that is something we need to be aware of. I think this mapping is the original Nanocomp mapping, and as we go through, then we'll see that some of these will be reversed. So the Darlington transistor array, which is replacing the original part in the Nanocomp diagram, this does actually have input resistors, so it has compatible TTL compatible inputs. The original design obviously had these resistors going into it for the MC6821, but we don't need to bother with that because it already has it. And you can see here, all this does is pulls this output C to ground. When there's 0 in there, then this will just be left to float. And as we said before, because the segments are pulled to 5 volts by default, then that means they will actually turn on. And this is more than capable of handling the current requirements. The keypad uses the same signals. You can see that the original keypad used the first 4 BCD decoder lines. Because the input port here, so PA to P7, PA to P6, because this will be pulled high by the internal resistors in the port, then by default, then this would read all 1s unless the current scan line was being scanned and went 0 and someone had pressed a key. So when we find a key being pressed, what we will see is a 0 will appear on port A, and on port B we'll then just need to know which of the scan lines we were actually using at the time. The keypad uses port A, port B, and the reset and the non-maskable interrupt line. So in fact the abort key does a non-maskable interrupt, and we'll look at how to wire that up on the 8088 a little bit later. So this is the exploded version of the keypad, and again there's lots of different ways of looking at this, and you'll see in 1 or 2 of the later slides I've color coded these to make things easier for testing, but I did these sort of combinations that when you're actually testing it with a meter or something like that, you can go through testing all the PA lines and see which keys were in there, and testing all the Q0, Q1, Q2, 3, and see what all the keys are on there. So this was just some of the intermediate stuff I produced for when I was testing things. And then this is actually the layout of the keypad. So you can see here that the reset and the abort are actually wired into those specific hardware lines. All the other keys here are actually just part of the scanning, and the color code here is basically the scan lines Q0 to Q3, so that's the port B values, and then it's just showing which colours are being used for the port A 0 to 5. Should note that the PA6 is not actually used in the keypad, it's only used in the 7-segment displays. So the colour coding on the wires and things I was using for the actual diagrams and things follow this scheme. So I'll put a copy of the PDF and things like that of the slides with the project in GitHub as well. And then finally, we do need to make sure when we're testing this that we make allowances for the old ENF mapping going to the new ENF mapping. Now I've updated the schematic diagram so that now ENF have been reversed, so we shouldn't hopefully need to worry about this. But when we come to run this up for the first time, if we find that some of these character values look a bit odd, then the chances are it's the ENF mapping which is the issue. So let's have just a quick review of the schematic. It's not too much extra that we need to worry about here. So we've got the peripheral interface adapter. That is going to be wired into the PLD over here where we had the PIA chip enable line. So the CS2, which is a low enables line, will be going to there. So that's how we enable that. We also need to map in A0 and A1. And in this design, I'm mapping RS0 to A0 and RS1. So that's something we need to worry about in the port mapping. Over here, I've got the serial port. So we'll be adding that in another video. So here we have the two 4-way 7-segment displays. So we've got going from Q0 to Q7. So from left to right. You can see here that we've got the 220 ohm pull-up resistors. So this means the 7 segments are on by default unless our Darlington driver here has a 1 coming in here and it will pull this particular input to ground and turn it off. So this was the main change that we had to make. So because our BCD decoder only has 10 output lines, 0 to 9, and we need 4 for the keypad here, and we need 8 for the display. So what this does is it decodes the 0 to 3, but then adjusts the output to the BCD decoder so that in fact 4 is 0, 5 is 1, all the way up to Q7, which will be 11. Now there might be other chips that had a 12-way decoder or 16-way decoder, but I had all these chips already, so this was just the easiest way to do it. I'm sure there's other ways of doing this. This allows us to get our 8 digits and the 7 segments to be used, and then down the bottom here we have the matrix where the port B outputs, decoded port B outputs, come on down here and port A comes here. And remember that port A on input is all pulled high automatically on the input of the PIA. So when a key is pressed, it ties that particular input line to ground. And again, whenever we're looking at bringing things in from the port, quite often we'll be inverting them, complementing them first to get a 1 where a key was pressed. Now the reset button and the non-maskable interrupt, the reset button will get wired all the way up to where the current manual reset button is, and that could potentially replace the reset button that we've already put on the board. Non-maskable interrupt needs to have a bit of extra logic put into it because the 8088 non-maskable interrupt is active high, whereas this is active low. So we will need to invert this, and I think what I'm just going to do is to probably make use of one of the inputs and outputs on this PLD here, or I might just add another inverter somewhere along the lines, but it doesn't really matter too much at the moment because until we have the monitor running, then we won't be doing anything with non-maskable interrupts. So it's something we can look at in future videos. So this is the 7-segment Keypad Decoder PLD, and I'll just show you quickly the configuration for this. I won't show you the compiling and burning this because I did that in the previous video. So we've got the inputs from port B 0 to 3, and we're really interested in the first 4 entries. So 0 to 3 are going to go out to the keyboard scan lines, and then the remainder of the lines are going to go out from P0 to P3. So the rules here just mean that Q0 is only enabled when all outputs are 0, Q1 when only PB is 1, all the others are 0, etc. So that just decodes those. And then we actually use this mapping table down here. We're using output 8 here as the invalid one. So when we get 0 to 3 for the keyboard scan lines, then we just enable 8. Then when we get 4, we enable output 0, 5 output 1, all the way up to when we get B, which is 11, we get output 7. Then any above that, then we just again enable 8. So all this does is automatically behind the scenes works out what the conditions are needed to do this. So all this is really doing is subtracting 4 from the input value to enable that the BCD value Q0 to Q7 is then actually providing the digit that we want. Now, to make life a little easier, then I've created chip labels, customized chip labels for the chips that we're using here. So the PLD here has the port B 0 to 3 inputs, then has the Q0 to Q3 outputs for the keyboard, and P0 to P3 going into the BCD decoder. And then there's a default ULN 2803, and then I've done one which has got the mapping. So I've actually got the mapping of A, B, C to G, and it has the correct mapping on here as well. And the E and F have been reversed in this particular one. So what this should mean is when wiring up port A to this, then it should just be a matter of following the label and putting the pins in. There's just a standard 6821 up here. So print those chip labels out, stick them on the chips, and then we'll look at how to lay out the board. Okay, so I've fitted the board here. Got a Breadboard Buddy power rail expansion here. I'm going to put a new power supply in here, but I need to solder those wires in a little bit later. And we've put the chip labels on, positioned the chips, I think, to where they need to be. So I'm just going to plug these in, and then we will wire it all up. And we'll come back once everything's wired in. Okay, so just going to put in the power lines for each of the chips and a decoupling capacitor for each of the chips as well on the close to the ground line. Then the feed from the rest of the computer for the power bus as well. Now we're going to put in the data bus lines for the peripheral interface adapter. Once we've done that, we'll put in the address A0 and A1 lines and the reset. And then we'll do the E clock signal, the chip select tied high, and the chip select coming from the PIA enable on the PLD. Check all those off. Now we're going to put the outputs from port B to go into the decoder. The PLD first, then the BCD decoder. Now this is the outputs from port A going into the Darlington driver for driving the 7-segment display. Check all those off. I'm just putting the power there. I did also put in a cable there in yellow for Q7. We're also putting P0 to P3. Check all those off. Now this is 7-segment display. Just going to plug that in as a block of 8 for all of the digit display things and the 7-segment display. Check all off. Now we're going to plug in the keypad, and that goes to the Q0 to Q3 and the PA outputs. Okay, so that's it. The keypad and the LED display all wired up. I've also wired in the power supply here, so that should give us good voltage down here. I will move the meter down here when we actually start to test this. Now what I am going to do is to just move this over a little and bring in the keypad. I have got some PCB mounts that I can put the keypad on. I'll just arrange the cables a little bit better than they are at the moment. Now what I'm going to do is to break the video here, and in the next video what we'll do is to look at writing the software to test all this. So what I'll be doing in the next video is looking at the fritzing tool plans which I used for the strip board design of the display and the keypad. And that's very helpful if you were wanting to try and make one of these yourself. Then those fritzing plans will be very useful for doing that. We'll then look at writing a test program using 8086 assembler. I was originally thinking of using C, but I think since I've already got 8086 assembler working, a simple test program to do hello world or something like that on the display, and also then to echo the key codes as they're pressed, would I think probably is going to be easier to do in assembler for the moment. We'll then program that into the EPROM, then check that the LED display and key codes are working, and then that should have us ready for us to develop the monitor in C, and that's probably going to need a bit more work to get the right tooling working and to get the C code running in the EPROM. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you found the content interesting and useful, please hit like. It just helps to make the videos accessible to a wider number of people. Thanks for watching.